For this lesson, we're going to take a look at some properties of limits. Now, these properties are important because they're going to allow us to evaluate the limits of functions without using the epsilon delta limit definition. So you'll find this a lot easier to use. However, we still needed that epsilon delta limit definition in order to prove all of these results. Now, we're not going to prove them in this video. We'll save that for another one. So let's start with this result. Some basic limits. So we're going to let b and c be two fixed real numbers. Then, first of all, the limit as x approaches c of b is equal to b. That makes sense. As x is getting closer to c, the number b is staying fixed at b. It never changes. So the limit must equal b. That's called our constant rule. You can see that rule if you want to think of a graph. Okay, so right here's our constant function b that crosses the y-axis right there at b. If I put c right here on the x-axis and x over here, and I let x slide towards c, you see the f of x values will always equal b. They will never change, right? Every f of x value is b, so as x approaches c, f of x will approach b, because it's always b. Alright. Let's take a look at this one. Limit as x approaches c of x is c. Well, that makes sense. As x gets closer to c, x gets closer to c. Now, here are some other properties that we need to look at. Now, for this theorem, once again, we're going to let b and c be fixed real numbers, and we're going to let f and g be two functions satisfying the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is k. Then we have the following. So first of all, we have what's called the scalar multiple rule. Limit as x approaches c of b times f. Well, what I can do is move the b outside the word lim, and then this part is just L. So my answer is b times L. Well, that makes sense. As x is getting closer to c, f is getting closer to L, so b times f is getting closer to b times L. Alright, well, that makes sense. The important thing to note here, though, when we work with some of these problems, is that you can move the b outside. Alright, next result. Limit as x approaches c of f plus or minus g. We can distribute the word lim to both f and g here. So you see we can write it as the limit of f plus or minus limit of g, and that's going to be L plus or minus k. That also makes sense. As x is getting closer to c, f is approaching L, g is approaching k, so f plus g is approaching L plus k, or minus. Alright. The important thing to note here is how you can move the lim with both f and g. Distribute it with both the f and g. Alright. We have the same rule for the multiple. Limit of f times g is limit f times limit g, or L times k. Same thing for we have a quotient rule. Limit of f divided by g is limit f divided by limit g. That's L divided by k. As long as the k does not equal 0, though, right? You can't divide by 0. Okay. Finally, the power rules. We have the limit as x approaches c of x to the n is, well, what you can do is you can move the limit underneath the exponent in with the x. So it's going to be the limit as x approaches c of x to the nth power, and that's just c to the n. In other words, you can just plug the c in for the x. Alright. And then finally, the general power rule. Limit as x approaches c of f of x to the nth power, you can move the limit in with the f underneath the exponent, like this. And then that's just going to be L to the n, because f is approaching L as x is approaching c. That was assumed.
Now let's consider how we use these theorems with a few examples.
Let's consider this one first.
Limit as x approaches 3 of 3x squared plus 2x minus 5. Now first, using property number 2,
we can distribute the limit with each term by the sum and difference rule. Now what we can do, you see these are constants here, like the b that was referred to in the scalar multiple rule, the 3 and the 2 right here. We can move them outside the word lim. Now also note that the limit as x approaches 3 of 5, that's just our constant rule, so this is just going to be 5, right? As x is getting closer to 3, the 5 is always 5, it never changes, so I can just put a 5 there. Now what we can do is use the power rule for these two right here. I can just plug the 3 in for that x, 3 in for this x, and we get
and we get 27 plus 6 minus 5 equals 28.
And that's our answer. Now you notice one thing here for this. If you look at how we have our answer written down here, it looks like we could have just taken this number 3 here and plugged it in for the x here and here. In other words, everywhere in our function, and just gotten our answer that way. We could have just plugged the x in. Well, yes, that's actually true for all polynomials, and that's a result that we'll state next. And that result is proven because of all of these results up here. Now let's take a look at another one. In fact, if you want to, you can pause the video here and try this one on your own. So I'm going to assume that you tried it already. So let's go through the answer. Now for this one, we'll distribute the limit to the top and the bottom.
That's by the quotient rule for limits. And next I'm going to distribute the limit to the x cubed, the 1, the 5x squared, and the 3.
And I'm going to pull that 5 out. Oops, it should be a 2. Oops, made a little mistake right there. Those should all be 2s. We're looking at a limit as x approaches 2. And now we can just plug the 2 in for the x. This is going to be 1. This is going to be 3. Put the 2 in for the x right there, and I get, and all of that comes out to be, let's see, 9 divided by 23. Okay, and that's our answer. Now also notice here, if you look at how this is written right here and compare it to what we have up here, you might just say, well, heck, we could have just plug the 2 in for the x here and the x here and just skipped all this stuff right in here, right? And just jump, we could have just jumped right from here to here. Why didn't we just do that? Well, that's true. You can actually just do that, and that's the result that we're going to state next. But I just wanted to illustrate how we actually use all of the results that we looked at previously to obtain that result that we're going to look at next. And that is that whenever you have a rational function, which is the quotient of two polynomials, you can just plug the c value in for the x and get your answer right away. So you can just skip all this stuff. But the reason you can skip all this stuff is because of all the theorems that we had earlier. Okay, now here are those results. For any polynomial p, the limit as x approaches c of p of x is p of c. You can just plug the c in for the x and get your answer. That's for any polynomial. For any rational function, which is the quotient of two polynomials, the limit as x approaches c of p of x over q of x is p of c over q of c. So you can just plug the x in, the c in for the x here, c in for this x, and you get your answer. Of course, that's provided q of c does not equal 0, right? You can't divide by 0. Okay. So let's take a look at some examples. Limit as x approaches 2 of 3x squared plus 5x plus 1. Okay, well, this is just a polynomial, so all we have to do is plug the 2 in for the x's. And let's see, that's going to be 12 plus 10, 23. This one down here, well, this is a rational function. It's the quotient of two polynomials. So, by the previous result, I can just plug the 2 in for all the x's. And let's see, what are we getting? We're getting here, this is 23, same as what we had earlier. Divided by 16 minus 2 plus 3, that's going to be 17. And there's our answer. Okay? So that's all you have to do for polynomials and rational functions. You can just plug your c value in for x. Alright. Let's take a look at this now. Limits of radical functions. So for n an integer, the limit as x approaches c of the nth root of x is the nth root of c. So you can just plug the c in for the x. Just one thing to note here, you have to be careful when this is defined. This statement is true whenever the nth root of c is actually defined. Now notice that the nth root of c is defined for all values c when n is odd, but it is only defined for c positive when n is even. Okay, so, and the reason for that is, for example, if I look at negative 8, oops, sorry, come on, there we go. If I look at negative 8 to the 1/3 power, that is defined. That is negative 2, because negative 2 cubed gives me back negative 8, right? So the cube root of negative numbers, that's fine. Just like the 5th root, the 7th root, they're all defined, okay? However, if I try to look at negative 8 to the square root, or the 1/2, the square root of negative 8, that's not a real number, right? There is no real number a in which a squared gives you back negative 8, right? There's no real number that does this, okay? There are complex numbers, right? This actually is a complex number, but we don't want to deal with complex numbers right now, okay? So we're going to say that this only holds for when n is even. This only holds for c positive, okay? Because the square root of negative 8 is undefined, just like the 4th root of negative 8 is undefined, and the 6th and 8th roots, whenever n is even, okay? By the same reasoning, like for the 4th root, there is no number in which a to the 4th power equals negative 8. No real number anyway, okay? Alright, so just take note of that. Let's just see why this is true. Like, why is this true? Well, graphically speaking, if you look down here, for example, right here is the graph of x to the 1/3 power. And you notice it's nice and smooth, and it doesn't have any breaks in it. So if I take a c value here, and right here would be the cube root of c, and I pick any x value, this little red dot right here would be the cube root of x. or x to the 1/3, notice that because this graph is nice and smooth, as try to grab that thing there. Well, just have to use my mouse. As I let x slide towards c, the f of x, or the cube root of x, is approaching the cube root of c, right? And from the other direction as well. Okay? As x approaches c, cube root of x approaches cube root of c. Okay, so this up here is true because the graph of the cube of the nth root of x, the graph of the nth root of x, is a smooth graph. Doesn't have any breaks in it. So let's take a look at this. So, for example, what would be the limit as x approaches 4 of the square root of x? Well, by the previous result, all we have to do is put the 4 in for the x. This one down here, well, once again now, technically we have to break this limit up, but you can just plug the 27 in for each x, right? So technically we break it up, but and that's just going to be 27, this part right here, by our radical theorem, negative 1/3 plus 27. So you can just plug the 27 in for the x's, and you get, let's see, what is 27 to the negative 1/3? Well, you have to remember that's 1 over 27 to the 1/3, positive 1/3, plus 27, and you end up with, this is 3 here, right? So 1/3 plus 27, and let's see, what is that? Well, think of 27 over 1 and cross multiply, right? 3 times 27, 1 times 1 over 3 times 1. That's going to be 82 over 3. There's your answer. Okay? You just have to plug the c value in for the x's. Right? Just plug this 27 in for the x's. Okay. Now let's take a look at the limits of trig functions. So for each c in the domain of the following trig functions, we have that the limit as x approaches c of sine x equals sine c. Right, so you just plug the c in for the x. Limit as x approaches c of cosine x is cosine c. And the same thing for all the trig functions. Okay. Limit as x approaches c of all your trig functions is whatever that trig function is evaluated at c. And the reason that is because same reason for our radical functions. The graph of these functions on their domain is smooth. It doesn't have any breaks. So take a look at this down here. So for example, right here is the graph of the sine function. So for example, if I have c right here on the x-axis, right here would be f of c, or the sine of c. Right? The blue curve, by the way, here is our graph of sine. Now if I pick any other value x on the x-axis, this value right here would be the sine of x. Right there, that red dot is the sine of x. Notice that as I let x approach c from either direction, sine of x will approach sine of c. And so as I let x approach c, notice the red dot is approaching sine of c. And the red dot is sine x. Okay, all right. So that result is true because those functions are smooth on their domains. Okay. Let's take a look at this. So evaluate limit as x approaches pi over 4, cosine x plus tangent x plus root x. Okay. Well, we can just plug pi over 4 in for all the x's. Okay. Technically, you notice that really when I do that, I'm distributing the limit with both the cosine, the tangent, and the root x by the sum and difference rule, and then I'm plugging pi over 4 in for each x, right? So technically I'm doing this. That's by our sum and difference rule. And then now you can just plug the pi over 4 in for each x to get and let's see, the cosine of pi over 4 is root 2 over 2. The tangent of pi over 4 is 1. If you're not sure of these, you can look them up on a table or use a calculator. And the square root of pi over 4 is just the square root of pi over 2, right? Just the square root. This is it's the square root of the whole thing here. So it's going to be the square root of pi over square root of 4. And then, you could simplify that as root 2 plus root pi over 2 plus 1. Okay. And then evaluate that on your calculator if you want a decimal expansion. All right. So that's an example illustrating how you use the trig limit results. Let's take a look at our final thing here for this lesson, and that is the composition rule. Okay, so limit of the composition of functions. So if f and g are functions in which limit as x approaches c of g is L, and limit as x approaches L of f is f of L, whatever that is, then you have the limit as x approaches c of f composed with g, or f of g of x, is f of the limit as x approaches c of g is f of L. Okay, so what this is saying basically is you can take the lim here and put it inside of the f and put it against the g, and then this part is just L. You get back f of L. All right. Now this makes sense. Let me just say this. This makes sense that this is equal to this over here, because as x is getting closer to c, the g is assumed to be getting closer to L. And so what's inside the parentheses here is getting closer and closer to L, and we know that if you take something and let it get close to L, f of that something will get close to f of L. So that's why we have this result. Okay, now let's take a look at some problems down here. Oops, I have one thing to fix right here. That should be a +1. Make that a +1 right there. Okay, so what we have here is let's take the limit as x approaches 1 of the square root of x squared plus 5x plus 1. Now what this theorem justifies doing is actually moving the limit underneath the square root. You see, for this problem right here, the f of x is really behaving, it's really the square root function. Okay, and the g of x is the x squared plus 5x plus 1. So what this theorem is justifying is moving the limit underneath the square root. Okay, let me write it like this. So it's going to be the square root of the limit x approaches 1 of x squared plus 5x plus 1. Okay, so you see, moving the limit under the square root is just like moving the limit inside the f, right? The f is the square root, so you're moving it inside. And then you can just plug the 1 in for all your x's here, because this is just a limit of a polynomial. And you end up with the square root of 7. Alright, so in other words, you notice if you look at this piece right here, you see what this theorem is justifying that you can do is just basically just take this x and, or this c right here, the c right here, and plug it in for the x here into your function. Just plug it in for the x's. You plug the c in for the x's, because right here it is. Okay, that's what this theorem is justifying. Now if you want, you could try this one. All right, if you want to pause it, you could try this one. I'm going to do it now, assuming that you already tried it. So now, in this case, for this function right here, just erase this here. The f of x is playing the role of the sine x. So let me put that over here. So the f of x is the sine of x, and the g of x is what's inside. It's the pi x squared plus pi over 2. Okay. So then what this theorem here is justifying is that you can move the limit inside and then get and then here you can just plug the 2 in for the x's, right? Because now you see this is a polynomial. Pi times 2 squared is going to be 4 pi plus limit of pi over 2. That's just a constant. So the limit as x approaches 2 of pi over 2 is just going to be pi over 2. And that is the sine of, let's see, 4 pi plus pi over 2, that's going to be 9/2 pi. And you can either evaluate this on your calculator or realize that the sine is periodic of period 2 pi. So this is going to be the same as the sine of pi over 2, which is just 1. Okay. And you see what we could have really just done here is you could really just plug that 2 in for the x here. And well, we don't have an x over here, so basically you would just plug it in for any x right in here. That's what this theorem is justifying. So I wrote it out like this, just showing you what the theorem is doing. But really, you can just plug the 2 here, your c, in for the x's up here. Okay? And you get your result. Okay, so that does it for this lesson on properties of limits.